In college, I was biking home from class and I got hit by a car hard. Here's a picture of the aftermath, but don't worry, the bike was fine, and after a couple unintentional flips through the air, I was able to walk away. This incident was the other driver's fault. I had a green light, but they just didn't see me coming. So I can't help but think that one, I got really lucky. It should have been worse. And two, if that same incident happened today, it might not have happened at all. The tech in the car could have seen me coming and intervened. The research for this type of tech is happening right now, and it's looking really good. Here's a peek at what it looks like. If you want to deep dive into these with the actual researchers, go sign up for Keysight World Innovate. There's a link, and watch the talks. Think like TED Talks for engineers, but I was watching these talks and my crash kept replaying in my head. And I get excited thinking that this new technology could prevent other people from going through what I went through. 94% of accidents are caused by human error. My accident was, and good systems, good automotive systems, could dramatically lower that number. There are a couple clever avenues of research in this space that I find fascinating. Here are three of them that were explored in depth during Keysight World Innovate, and I'll break them down a bit for you here in this video. The first clever engineering trick uses invisible waves, not the ones you're thinking, not electromagnetic waves, but sound waves to see around corners. It kind of takes me back to Magic School Bus. Sound is one of those things you don't think about when you're driving, but then when a song pops on the radio and there's a siren in it, you're like, oh, where's the cop? Am I getting pulled over? Is there an ambulance? Oh, it's just a song. So sound is important for driving, and we can use it to see things that we can't see. This is a big challenge with advanced driver's assistance systems, or ADAS. It's that you can't see around blind corners. There are proposed vehicle-to-everything systems, or V2X, that could use basically like cell phone pings to figure out where other cars and pedestrians are, but this method works without 6G or V2X networks. It simply uses a microphone array on the vehicle, so you can hear what's coming. And if you're a clever engineer, and if you're watching this video, you probably are, you can even use reflection patterns like this. There's a car coming from the right, and the sound is also reflecting off of the wall. So you could train a machine learning algorithm on what a car sounds like. Turns out over 30 miles per hour, it's just tire noise anyway. It doesn't matter if it's an EV. And then use other systems to know there's a wall there, and figure out there's a car coming long before your LiDAR or your cameras would pick up that other car. An entire second sooner, based on this research from Dario Gavrila, head of Intelligent Vehicles Group and a professor at Delft University of the Netherlands. This same group is also using dynamic Bayesian networks to predict what pedestrians and cyclists will do a few seconds before they actually do it. If you know what they're going to do, you know how the vehicle should respond. Now, I confess, I had to look up what a dynamic Bayesian network is. I'll spare you the gory details, but it's pretty cool, and this is something you're going to hear more about in the years to come, so you might as well get the crash course on it now. No pun intended. Basically, a Bayesian network in this type of application lets you predict what's going to happen based on a set of weighted variables. Take a pedestrian, for example. How close to the curb are they? How fast are they moving? And in what direction? These are each variables and pretty obvious clues about what they're going to do. For example, if there's a pedestrian 10 feet away from the side of the road and not walking towards the road, they're probably not going to be something your vehicle has to worry about. But what about more nuanced things? If they're coming towards the road, like, are they looking at you, at the car coming, or are they looking somewhere else? That's a variable. What about their body position? Are they going for it, like, Abbey Road Beatles, or are they slowing down? Or other vehicles. If another car has their blinker on, we need to weight that heavily in our Bayesian network because that car's probably going to turn. These are things we inherently understand as human drivers, but we need to specify each of these as variables in a Bayesian network. Bayesian networks also have latent variables, which are things you can't directly observe in the moment. It's kind of like a state switching on or off. For example, a cyclist wanting to take a turn, they hopefully signal with their arm left or right, but then they put their arm down because they got to get their hands on the bars to make their turn. The fact that they signaled with their arm is important, and it should be a weighted variable even if they aren't actively doing it in the moment that they're about to turn. It's kind of state machiney, but with like probability weightings. And an expert in Bayesian networks and machine learning can lay out all the variable relationships and weight variables appropriately to predict what's going to happen. Will that pedestrian step into the street or not? And then a dynamic Bayesian network, or DBN, adds the word dynamic because it includes time, which is helpful because we live and drive through time. So a DBN is an expert-driven prediction model, which is nice because first, you get those latent context variables. Second, it only takes tens or hundreds of variables to be effective, have a good system. And three, you can explain how it made its prediction. You can trace the math, and that's a really good thing for safety and traceability. A DBN is different than a data-driven model like a neural network or a transformer. Those need tens or hundreds of thousands of parameters, and you don't really know specifically how it arrived at a certain answer. A data-driven model has proven to have better performance if you have sufficient training data, and that is a huge, huge challenge. So DBNs are worth researching. So here's a DBN in action thanks to Professor Dario at the Pantheon in Rome. It's tracking people, and this is a nightmare driving scenario for me, but it's something that a level 5 autonomous driving system would have to handle without any driver input, even in the snow or the rain. A more simple case is this one. We know Blue Fella is not going anywhere, but what about these other two? Brown is approaching the curb, but it looks like he's slowing down and probably looking at the car. These are all variables in our DBN, and the DBN chooses which context variables matter here. Which ones are we going to use? And we predict he's going to stop, and it turns out he does. This joker over here, though, he's not looking and he's still walking right out into the street, and our context variables become very important, and the vehicle decides to stop so we don't take him out. A win for autonomous driving. Another area of research, one of the Keysight World Innovate talks by Chris Gerdes, a professor at Stanford. You might remember his drifting DeLorean from my video last year. This one's basically summed up as a race car go fast, vroom, vroom. Yeah, I wrote that into my script. So if you want to be more formal, that's vehicle dynamics. So remember the guy who wasn't paying attention and walked out in front of the car. Our DBN decided he wasn't going to stop, so now we have to stop or plot out a route around them. But how fast can we stop? How sharp can we turn? What if it's windy or rainy or snowy or the tires are bald or any number of variables? The car we're in needs to know exactly how far it can push itself before the wheels lock up. Wheels locking up is bad for traction and performance. So you have what's called a friction circle. Each of your tires gets about a palm-sized connection with the ground. That's it. And we want to take full advantage of that patch of tire. So Chris and his team are able to real-time plot the friction circles of each tire while autonomously ripping around a racetrack. The line is like a force vector for each tire, and the circle is a limit of how much each tire can be pushed. The size of the friction circle changes based on how fast the car is moving. For example, a left turn means more friction on the right tires because there's more weight there. You don't want your vector or your line to go outside the friction circle or you lose traction in that wheel. If you lose traction, you can't turn as sharply or stop as fast. Their test car can brake each wheel individually and update braking forces about 200 times per second, making real-time route planning and braking decisions. So, if your model is telling you that someone's going to walk out in the road in front of you, you can now plot a new path and do everything physically possible to avoid them. I'm a decent driver, but I am willing to bet hard cash that machines could do it better, especially these machines that they showed off at Keysight World. With systems like this, which exist now and are getting better and better, thanks to these folks like Chris and Dario and their teams, we can dramatically reduce incidents like this. And hey, maybe people like me who are riding their bikes through green lights won't get hit in the future. If you stuck around for this whole thing, you definitely should go sign up for Keysight World Innovate and watch the full talks. It's all 100% free, and this was just my personal highlights from one session. There's a lot more there on a lot more topics. I'll put an easy link there for you, so go check it out. And don't drive like my brother. Probably don't drive like Big Brother either, but drive safe.